Hello! We've reached the most exciting part of Chapter 11, as in this video we will do some programming. More precisely, we will try out the AD converter on the STM32F446 microcontroller. If you've got a Nucleo development board at home, just prepare it and we'll get started.
In this example, the voltage value at the output of the potentiometer will be measured. To do this, we will use the AD converter of our development board. The converted value will be displayed in digital form and converted to voltage. The circuit we have built is shown in the figure. The potentiometer is placed between 3.3 volts and ground potential, and the middle voltage divider leg is connected to one of the ADC legs of the microcontroller. In addition, you can see a schematic of the OLED display with the wiring already learned and applied. Of course, if you use a different microcontroller, you may have to connect each component to a different leg.
Once the connection is set up, let's see how the ADC peripheral is managed. First, we configure our ADC module using the CubeMX graphical interface that we have already learned in Chapter 4. We have connected the output of the potentiometer to the PCO leg, so we need to configure this leg as an analog input and name it, for example, HMI_POT. Next, in the analog menu of the left-hand menu bar, under the ADC1 settings, you can specify the configuration you want to use for the peripheral.
Let's see what parameter setting options are available. We can set our clock prescaler, which affects the clock speed of our peripherals. The ADC peripherals are set to PCLK2 clock, the maximum value of which is 84 MHz for the microcontroller on the development board. We use 16 MHz for the task. This can be divided by 2, 4, 6, or even 8. We will use division 2 for this project. In the next line, you can select the resolution, how many bits you want to convert. By default, the conversion is set to 12 bits, but this can be set to 10, 8, or 6 bits. In which case the conversion will of course be faster, as fewer ADC clock cycles are required. The data alignment will determine whether the 16-bit register's upper or lower 12 bits will contain the result. We now choose the right alignment. Then, we will get the result in the lower 12 bits. The remaining upper 4 bits of the register will take the value 0. We also need to select the ADC mode, which in the first example program is a single conversion, that is, the continuous conversion mode should be turned off. The other options described earlier are turned off as well. We also need to specify an event to indicate the end of the conversion. This can occur when the conversion of each channel is finished, or when all conversions have been completed. Since we only use one ADC channel anyway, we can use the former option.
In the next drop-down menu, regular conversion mode, you can specify the number of channels you want to use, which in this case is 1. You can set the conversion process to be triggered by an external trigger event or by a predefined method initiated by software. For example, an external interrupt can be generated by the microcontroller's hardware timers to start a conversion at an expiry time, saving some operations compared to if the same had been done with a software timer. In case of a software-triggered conversion, the process will be started by a function call. How to do this will be explained a bit later. When using multiple channels, we will have to rank each channel in ascending order of conversion. For example, if we want to use ADC channels 5 and 8, we can set the conversion of channel 5 to be performed first, and then channel 8. Finally, you can see on the screen that for each channel, we also need to specify a sampling time, which is in ADC clock cycles. This means how long the capacitor of the ADC input buffer will be charged before the sampling of the signal. Of course, the higher this number, the more accurate the result, essentially an averaged value, although it will take more time.
In the generated project, we can find the part responsible for initializing our ADC peripheral in the adc.c file. Let's look at this in more detail. The HAL library provides us with an ADC handle type def structure that helps us to easily use the ADC peripheral. This structure is where we store the configuration for the ADC and where the functions provided by the library operate. We have created a global variable of type ADC handle type def named ageADC1. You can see the configuration code generated for the ADC peripheral under mx ADC1 init, which contains the parameters that were specified in the graphical interface. The instance element of our ageADC structure contains which ADC peripheral of our microcontroller the configuration parameters will belong to. In this case, it is ADC1, which is essentially the address of the register through which we can access the first ADC peripheral of our microcontroller. Next, we can see the items to initialize, all of which are located under init. The HAL ADC init function performs the configuration of the ADC peripheral. Running it will put the desired configuration into the appropriate register. The parameters of the channel to use are specified in a structure of type ADC channel conf type def. This stores the channel ID, its ranking position, and how long the signal will be sampled during the conversion. The previously compiled channel configuration is passed to the HAL ADC config channel function. The GPIO leg of the channel to which the ADC is connected is also physically initialized. It's found within the HAL ADC MSP init function. This is where the clock for the ADC and I/O peripherals is enabled. In the structure of the GPIO, the identifier of the leg must be specified under pin, and the mode must be determined to be used in ADC, that is analog mode without pull-up resistors. The configuration is validated by calling the HAL GPIO init function with the I/O configuration we have just assembled.
We use the functions to initialize the I/O leg to be physically used and the ADC peripheral itself. The ADC module of the microcontroller is then ready to use. Let's go to the main.c file and have a look at our program. In our first example, we use our ADC in blocking mode.
To start the conversion in blocking mode, you can use the HAL ADC start function, to which you must pass the structure representing the previously configured ADC peripheral. This function also contains error handling, which checks, for example, whether the peripheral is even on. If not, the ADC is first turned on. But how will we know that the conversion is complete? This is done by the HAL ADC poll for conversion function, which takes the previously used ADC structure as a parameter and the timeout value. This indicates the maximum time in milliseconds to wait for the conversion to finish. In our example, the value passed is 10, so we wait for a maximum of 10 milliseconds for the result of the conversion. To illustrate, in this time, at the maximum conversion rate mentioned earlier, 2.8 MSPS, 28,000 conversions would take place. If the operation finishes before the time limit is reached, we return to the main program immediately. If the timeout has elapsed, the function exits with an error and the conversion has failed. The result is obtained from the ADC DR register, which is read using the HAL ADC getValue function, and then its value is displayed on the display. I think we are ready to program our device.
I've already compiled the project and I am starting to upload the code to the device. Let's see what we see when the programmer is done. Right now the programming is in progress, and it's done. If everything works, the display will show the ADC value on the top line of the small OLED display. Below that you will see a numeric value between 0 and 4095 and a value between 0 and 3300 mV. As you turn the potentiometer, the value changes. Let's try it out. You can see that if I turn the potentiometer to the left, the value decreases, and if I turn the potentiometer to the right, the value increases. But don't think we are done with this.
That's correct. The program just presented, while simple, has a significant drawback. The microcontroller waits for the ADC to complete its measurement. Now, let's examine a program that utilizes the ADC peripheral in interrupt mode. This approach allows the microcontroller to perform other tasks while the conversion is taking place. The conversion result will only be read after an interrupt signals that the conversion is complete. Let's first go back to the CubeMX interface and enable interrupts for the ADC peripherals. You can do this in the interrupt controller settings, or NVIC settings for short, meaning nested vector interrupt controller settings.
Returning to our program, the interrupt is initialized in the HLADC MSP init function as follows. During initialization, you must assign a priority to the interrupt or enable the interrupt itself. In more complex software, where multiple interrupts can be used, it makes sense to set the appropriate priority order.
Once we are done with that, let's go back to the main.c file again. In this case, we can start the conversion by calling the HAL ADC start IT function. Within this, the ADC interrupt is enabled. Bit manipulations in registers are performed in a similar way to the previous case. After the function is done, the microcontroller continues executing the main program and does not wait for the result. At the end of the conversion, a hardware interrupt is generated by the ADC peripheral, which calls the ADC IRQ handler, and within it, the HAL ADC conv CP IT callback function, which we have to write. Since the callback function doesn't know which peripheral has called it, the passed AgeADC pointer parameter will always point to the local AgeADC variable in the declaration. If, for example, AgeADC1 or AgeADC2 were written specifically, it would return the result only for that peripheral, ignoring which ADC calls the callback function. We put our function that reads the result of the conversion in the callback function because every time it runs, we can be sure that we will get the result of a new read. If we need to, we can call the HAL ADC stop IT function to stop the AD converter. But it is not included in the example code.
The code is now ready. Compile it and run it. Let's wait for the programmer to complete it.
I see it's been updated.
That's right. What we can see is that from the point of view of the average user, if we look at the way it works, there is not much difference. However, we know that the code is much more optimal than the previous case. But if we consider the average user, they, and probably you too of course, will notice that the value changes and jumps a bit even if the potentiometer is not touched. The measurement is therefore a bit uncertain and inaccurate.
This inaccuracy may be due to internal errors in the ADC or measurement noise. Fortunately, there is a simple solution to improve this somewhat by increasing the sampling time of the ADC. Set the ADC channel sampling time to 480 clock cycles in the CubeMX device setup interface, then regenerate the source code after saving. In ADC.c, you can see that the channel configuration has been changed from the previous 3 cycles to 480 cycles.
So essentially, we will get the average of 480 consecutive time instants of the signal. Let's see how our modified code will perform. To do this, compile the code and upload it to the Nucleo board.
The LED is flashing, so it's in progress. Yeah, the screen has just been updated.
That's right. And you'll see that the values jump a bit less on our little display. Now the question is, are we satisfied with that, or do we want something even better?
Well, I think that if we've come this far, the last thing we should do is to make a program that does a bit more sophisticated averaging than the previous solution.
Let's calculate a moving average. This means that our current result will always be the average of the last measured value and the specified number of measured values before it. In our example, this average is calculated from 25 consecutive converted values. To calculate it, we need an array, a variable containing the moving average, and a pointer to keep track of where in the array the result of the last conversion was placed. This indicator is incremented after each conversion. Exactly 25 conversions later, we will return to the first element of the array, so that only the most recent 25 values are always included in our array.
In the main.c of this program, we first create the necessary variables, this time globally. The ADC average array will store the results of the last 25 measurements. The pointer p_average_cnt will point to the last modified element, and the average of the array values will be stored in the variable avg. In the while loop, the ADC starts in blocking mode, and then the conversion is checked to see if it was successful. If so, the result is read and stored in the appropriate location in the array. If the pointer extends beyond the array, it is again returned to the beginning of the array. After saving the value, the index variable is incremented, and the variable used to store the average is reset. Finally, a for loop is used to sum the elements of the array, and then we divide by the number of elements to get the average. But as the saying goes, the test of code is to run it, so let's do that now.
Just a moment, I'll start the compilation and upload the code to the microcontroller. The program will be done soon.
I hope the LED is flashing.
Yes, it is.
And the LED lit up.
That's right. And now let's take a look at what happened. We can see that this gives a more stable, slower changing value on the display. However, you can observe that when the potentiometer is turned, the new value changes much more slowly compared to the previous examples. This is because the change is detected later by averaging. This has affected the accuracy of the measurement in a positive way, and also has successfully reduced the magnitude of the excursions, albeit at the expense of the speed. I think our little program has achieved its goal, and we can close chapter 11 now. In this chapter, we have been introduced to the ADC peripheral, first in general, and then specifically for this STM microcontroller, and then we have tried it out in practice.
We hope this chapter has helped you understand how ADCs work, and that you are inspired to apply what you have seen in this video to your own projects. We recommend that you also read the written version of the chapter, where we go into more detail with a few insight blocks, for example, what the flaws are in measuring with an ADC, because like everything, unfortunately, they are not perfect.
Please check out the other Crystal Clear Electronics 2 videos, because there are many more interesting topics to be presented. Join us next time.
Goodbye.